So I have this codimension 2 submanifold sitting in a high dimensional space. There's a mean curvature vector which sits in the 2-dimensional normal space. Because the normal space is 2-dimensional, and I guess I want to assume the manifold is orientable, I can define, if the manifold is orientable, I can define in a consistent way a notion of rotating I want to rotate by 90 degrees in the positive direction. Rotate by pi/2 in the positive direction in the 2-dimensional normal space. And so this, of course, is, so in R3, I have a 2-dimensional normal space, and I can rotate in 90 degrees, and that's what the I should look back up here. So you see here, this is the unit tangent, and this is what's called the normal curvature vector, and these are orthogonal. By this condition, if I differentiate this, I'll find that dSS of gamma is 0. So these are 2 orthogonal vectors. This is the unit vector. If I take the dot product or the cross product of this second derivative with this unit vector which is orthogonal to it, that just means I rotate by 90 degrees around the tangent vector. So it's a 90-degree rotation in the normal space. And of course, the curve is oriented by the tangent vector. Okay, and so the natural generalization is exactly the same. I have this oriented codimension 2 submanifold. I have this mean curvature vector, and I rotate by 90 degrees in a way that's prescribed by the orientation in the normal space. This is sometimes called the skew mean curvature flow. And so there'll be a talk on well-posedness for this. So the existence uniqueness, etc., for the standard binormal curvature flow, the flow of curves in R3, is pretty easy. It's very classical. I think that was first proved by my colleague Catherine Soulem in the 80s, maybe, and collaborators. But that's not hard. And for the skew mean curvature flow, this is the flow was introduced a while ago by me, actually, and then in the context of gross perspectivity, re-derived in the context of Euler by Boris Kaysen and a guy named Banavar Shashikant, and so there'll be a talk on that well-posedness. That's Wednesday morning, I believe. No, that's Tuesday morning. There it is, Tuesday morning at 9 o'clock. And then there's also a talk by Boris Kaysen on, and so Boris will give a symplectic perspective, say. On the binormal curvature flow and the skew. So the version in R3 and the higher dimensional analog. Okay, great. So that's one theme that we'll see quite a lot of. Okay, another theme. So if one wants to derive these equations, the binormal curvature flow from Euler or especially from Euler or in Navier-Stokes, one might also expect to see these kinds of phenomena, then you have to consider these equations with initial data with very concentrated vorticity. And this leads to challenging questions, even of basic existence results. And so there's some well-posedness. Questions with concentrated vorticity. For Navier-Stokes. And that'll be the very first talk, Pierre Germain, at 10 o'clock today. And then there's one by Thierry Gallet. What's he talking about? I think it's also Navier-Stokes. Actually, right. And so he's talking about axisymmetric equations. And So he wants to, so we use it in particular to determine the translation speed of the vortex string beyond the binaural flow approximation. And so this is the, I think they want to consider axisymmetric flow with swirl. And so this is a regime different from the one we've been talking about, and one in which corrections to the binormal approximation should appear. So also, so this is Germain, axisymmetric with swirl, and that's Gallet. Okay, so a different theme is construction of, well, okay, so let's say actual vortex dynamics. So this is something we've actually talked about at some length. And so there'll be two talks that I recommend to you. One is on a construction of solutions that exhibit vortex leapfrogging. This is Juncheng Wei. And when is this? I think that's oops, wrong direction. I need to, oh, there it is. I need to go back. Can you hear this incredibly annoying noise? It's louder elsewhere in the house. Okay, so yeah, Juncheng Wei on Wednesday, and actually these are both Wednesday morning, Juncheng Wei and the lake equation, Jean van Schaftingen. And so van Schaftingen will prove a generalization of the result that we've been discussing, this result about translating solutions of Euler for the lake equation, which we've also discussed. And so these are both Wednesday morning, starting at 10. Okay, so another theme that we'll see some of is there's a construction of flows exhibiting vortex filaments of prescribed behavior. And so this is, there are two talks. One is Peralta Salas, and one is Enciso. So what do I mean by this? Well, let's take a look at the at Peralta Salas. And so here's what they want to do. And so, for example, let me discuss. In fact, these guys are collaborators, so they'll be talking about related projects, or about two. I think Peralta Salas will talk about joint work with Enciso and vice versa. So a well-known result of theirs from some years ago, which is not the one they'll talk about, which is in the same spirit, is they look for they want to show that for stationary solutions of Euler equations, that if you give me some knot, like a trefoil knot, or just choose any knot from an atlas of knots, they construct solutions of the Euler equation, the stationary Euler equation, that have a vortex filament exhibiting exactly that knot type. And so they can do this for arbitrary knot types, and they can be, there can be multiple knots in different places and so on. And so this, in some ways, is a regime for the Euler equations that's quite that's almost orthogonal to the one in which in which I'm concentrating. So it's so in other words, the solutions they construct are solutions who have lots of vorticity everywhere. They're kind of they're maybe large solutions. They're the vorticity is not all concentrated. But within this very complicated vorticity, they can find exactly one or a handful of vortex filaments whose behavior they prescribe. And so it's unconcentrated vorticity within which they can prescribe behavior. But they have very interesting techniques. They come from dynamical systems, and they're certainly related in spirit to these other questions about vorticity. And so, right. So a big issue in these in this general area is the question of reconnection, which I've shown you pictures of this, I believe. But reconnection is if these two filaments collide and they change topology upon collision. And so, and Caesar will talk about constructions of the solutions to the gross Pdf's equation, in which the vorticity exhibits sort of prescribed reconnection events. And again, they're tracking, say, one vortex submanifold within a larger flow about which not so much information is available. So they start by constructing the solution in a tiny neighborhood of the thing they want to construct, and then they approximate it by a global solution who is close to the given thing. But they're very interesting results. Another place where reconnection appears is this. So nearly parallel filaments. Okay, so I've described several regimes when we hope to know what vortex filaments are doing. One is this fully, the one I've just discussed earlier today, this binormal curvature flow. And then there's if I have 2D point vortices, which is the same as 3D. These are vortex configurations in 3D whose translation is variant in the vertical direction. Then they evolve by an ODE. Essentially, each one generates a flow, and then they get convected by the flows generated by the other guys. Okay, so an intermediate regime is, well, first a regime that's, I could take the full binormal curvature flow and look at a filament who's a small perturbation of a say a vertical line. So I take a vertical line and I look at a small perturbation, and what one expects to get from that is a kind of a linearization of the binormal curvature flow. And that's exactly what is predicted. And the linearization turns out to be exactly the linear Schrodinger equation. If I write, so at each height, say z, I write the displacement as a complex vector. And then I do some rescaling. And so then I have a complex valued function of z and t. And this binormal curvature flow, and once you linearize, turns out to be, well, the curvature turns into the second derivative with respect to z, and the rotation by 90 degrees turns into multiplication by I. And so if I just take a straight filament and I perturb it a bit, then one expects the limiting flow in a certain regime to be exactly the linear Schrodinger equation. Now suppose I take more than one filament, and if they were straight, they would interact by this ODE. If they're slightly perturbed, then they solve this linear Schrodinger equation. And so there's a regime where these two effects are of comparable magnitude, and there's some conjecture is so that each so I would. And there's some constants someplace. Okay, so I have a piece here who's the ODE piece. This is the interaction piece, and I have a piece here who's the linearized curvature piece. And so this has been proved to hold for the gross Pdf's equation, and it's not known for Euler. It's a hard question for Euler. But there are questions, and so this was derived in part because people wanted to look at this reduced system and see the approach to vortex collision in this setting. And so, but this system too is of interest, and so there'll be a talk of Mio, Evelyn Mio. When is that? That's Friday morning, 9 o'clock. And she will talk about, I think she'll construct solutions to the system in which collisions occur, and she'll describe the approach to collision and so on. And so that's an interesting talk. And then let me just say about the others. Well, okay, then there's a category, other. Which, and so these are kind of diverse. This would include this talk, Besaya, this afternoon. Susana Gutierrez, Protash, Bartek Protash from McMaster. Maybe that's oh, and Manuel Del Pino. Also, when is Manuel? He's the second talk this morning. And so Manuel will talk about things that actually are not very related to vortex dynamics, but the techniques he uses are the same ones used in the work of himself and Wei and collaborators on leapfrogging, which will be discussed by Wei in a couple of days. So that's a rough preview. Let's see. Are there any questions about anything? And so as to which talks will be accessible, it's a bit hard to say. So any of these could be presented in such a way as to make it incomprehensible to non-experts. And so, or not comprehensible to non-experts. The talk of de la Hoz is likely to have pictures and numeric. I mean, so these guys, they're very interesting conjectures. So the questions here have to do with, well, let me see if I can find all right, I'm going to stop sharing this screen and start sharing a different screen in a second. If I can find something. Okay, good. So hold on. Okay, so you should now see the screen of my desktop. And what I want to show you are some of these movies. And so I'm not sure which one of these will work. I don't remember. Okay, and so one thing we can do is we can solve the binormal curvature flow with initial data being a square. And so remember, the law of motion is for a smooth curve, I measure the curvature and I move in the direction that's orthogonal to, so for a planar curve, I would move in a direction orthogonal to the plane in which the curve is sitting. And so here the curvature is 0 everywhere except at the vertices where it's a delta function, at least initially. But you can put it in the computer and simulate it, and you get okay behavior, nothing very crazy. And de la Hoz and Vega have carried out very careful numerical and sort of analytical studies to predict this. And so one thing you see is that at certain times, like at the time it stopped, the flow again appears polygonal. And other things you can see is, I mean, if you look at the level, so this was for the flow itself. If I look for the, if I differentiate and look at the behavior of the tangent vectors, then you see earlier I had a square. And so on each side of the square, the tangent vector is constant, and then it jumps to a different constant. And so here, although it looks the same, it's a different picture. The last picture was a piecewise affine. This is piecewise constant. It spends all of its time at one vertex for pi over 2, and then it jumps to the next vertex and stays there for pi over 2 units of arc length and so on. And also to get to the tangent vector from the equation, I differentiate once. And when I differentiate, I expect things to get less regular. And indeed, let's see what happens. Yeah, so it has a kind of crazy fractal-like behavior. It's going to stop at the same time the last animation stopped at, when the flow itself appeared roughly polygonal. And so we can see here the tangent vertices, the tangent vectors, are concentrated around maybe 12 points on the sphere, corresponding to a 12-sided, a nearly 12-sided polygon in a three-dimensional space. And so this is what, these are the kinds of things that de la Hoz will talk about from a probably numerical perspective. They have much more careful numerics. What I'm showing now are simulations based on using code written by my friend Didier Smets. And de la Hoz and Vega have both simulations and some rigorous results of Vega that point in this direction. Okay, so that's all I have to say for today.